Hello there, and welcome to the Sleepymentary channel. Tonight, let your mind drift into a quieter place, one where the universe unfolds slowly, gently, like a deep breath taken among the stars. In this calm corner of the night, we're going to explore one of the most mysterious ideas ever imagined: spacetime. It's a concept so simple in words, yet so endlessly confusing in reality, that even Einstein, its creator, spent his life trying to understand it. We can watch spacetime bend around black holes, feel its effects in our GPS signals, and even detect its ripples passing through Earth, and still its true nature slips through our fingers. So, as you settle in, allow this story to move at the pace of your breathing, steady, soft, and full of wonder. We'll walk together through the ideas that changed physics forever, ideas that reshaped our sense of time, motion, gravity, and the very structure of the cosmos. And with each step, we'll lean a little closer to the heart of the mystery Einstein left behind. So, before we continue, hit like and subscribe so you don't miss a single revelation. As this story unfolds moment by moment in real time, tell me in the comments where you're watching, from what time it is there, and whether you believe we're hearing the whole truth about what's unfolding above our heads. And if you want to keep the signal alive, share this video on X, Facebook, Reddit, or even just with the people who still look up at night. You are the reason we can keep following the impossible, and for that, thank you. This is your quiet journey into space-time, an invitation to dream while discovering the universe. Let's begin. Space-time. A simple idea that confuses everyone. Tonight, as the world around you quiets and your breathing begins to settle into a calmer rhythm, let us wander together into one of the strangest, most beautiful ideas ever proposed by the human mind. It is an idea so simple that you can describe it in a single word, spacetime, and yet so confusing that more than a century after Einstein introduced it, we are still trying to understand what it truly means. If you step outside right now and look up into the soft darkness of the night sky, you may feel what countless generations before us have felt: the sense that space is just emptiness, a vast dark stage where stars, planets, and galaxies quietly perform their distant dances. And perhaps time feels like something even simpler, a steady tick-tock, a gentle current that carries you from one moment to the next. Ordinary, familiar, unquestioned. But the deeper you look, the stranger it becomes. Einstein dared to whisper something that sounded almost impossible: space and time are not separate things. They're woven together into a single entity, space-time, a fabric so subtle, so delicate, that it shapes every movement of the universe. And even now, with all our telescopes, satellites, detectors, and equations, the truth is that we still do not know what spacetime actually is. We can measure its behavior, we can watch it curve and stretch and ripple, but its essence, the thing underneath the mathematics, remains hidden. It is a mystery that sits quietly at the heart of modern physics. Imagine for a moment a calm lake at dawn. The surface looks still, like a flawless mirror reflecting the sky. But drop a single pebble and waves begin to ripple outward, carrying the imprint of that tiny disturbance to the far edges of the water. Spacetime in a way behaves like that lake. Massive objects, stars, planets, even you, create gentle depressions in the fabric. And when something violent happens, like two black holes colliding, spacetime rings with ripples that travel for billions of years. These ripples, these tremblings of the universe itself, are what scientists call gravitational waves. In 2015, humanity heard spacetime vibrate for the first time. Two enormous black holes spiraled together long before Earth even existed, releasing more energy in a fraction of a second than all the stars in the observable universe combined. And when their final crash sent a shiver through spacetime, it traveled across the cosmos until it brushed past our little planet, whispering into the arms of detectors built with almost impossible precision. LIGO registered a distortion in length smaller than 1/10,000 the width of a proton, a measurement so delicate that even the slightest noise on Earth could have overwhelmed it. Yet the signal was there, a soft cosmic heartbeat, a confirmation that spacetime is not just a clever idea, it is something real, something physical, something alive in a way no one expected. And yet, we still do not understand it. Consider this: we can see spacetime bending light itself. When a massive object sits between us and a distant galaxy, it warps the light passing by. The galaxy behind it suddenly appears stretched, curved, or multiplied, as though the universe were bending a lens to magnify its own secrets. In 2019 and 2022, when the Event Horizon Telescope captured the shadows of black holes, MIT 17 and Sagittarius A, Those blurry glowing rings were not just pictures, they were portraits of space-time under extreme pressure, showing us how light behaves when the very structure of the universe is twisted around a monstrous mass. The images matched Einstein's predictions almost perfectly. And still, we do not know what space-time is. This uncertainty is not a failure. It is an invitation. Throughout history, the most transformative scientific ideas began as mysteries, questions so large and so persistent that humanity had no choice but to follow them. Space-time is one of those questions. It sits quietly at the boundary between what we know and what we hope someday to understand. When physicists describe space-time, they do not talk about it the way you talk about objects or materials. They describe its geometry, its shape, its curvature, its stretching and shrinking. They describe how clocks tick differently depending on where they are in this fabric. They describe how objects naturally follow the straightest possible paths through space-time, even when those paths appear curved in ordinary space. But none of that tells us what space-time is made of. Some believe space-time is continuous, smooth, like an infinitely flexible sheet. Others think it is granular, made of unimaginably tiny atoms of volume, each a quantum pixel of reality. Still others believe space-time is not fundamental at all, that it is an emergent property, something that appears only when vast networks of quantum information entangle in just the right way. One prominent theory suggests that space-time behaves like the surface of a hologram, an illusion produced by deeper laws living on a distant boundary. Another proposes that space itself is nothing more than the shadow of entanglement, the way relationships between quantum particles create the illusion of distance. There are even whispers that space-time is not a thing but a process, a dynamic unfolding, like a story being written moment by moment. And yet despite all our theories, experiments and equations, the truth remains as elusive as ever. But perhaps that is the beauty of it. Tonight, as you listen to the quiet rhythm of your breath and let your thoughts drift into the gentle darkness behind your eyelids, consider this: there is something profoundly human in our desire to understand space-time. We do not study it because we expect simplicity. We study it because it represents the edge of our understanding, the place where curiosity meets humility. Einstein once said, "The most incomprehensible thing about the universe is that it is comprehensible." And yet here we are confronting a concept that resists comprehension at every turn. Space-time is both familiar and alien. It holds us, shapes us, carries us from birth to death. Every moment you have ever lived exists because space-time allows moments to flow. Every place you have ever walked exists because space-time makes place possible. You are a child of this fabric, woven into its geometry, carried gently along its currents. And still, the fabric itself remains unknown. Perhaps that is why this mystery is so soothing to explore at night, when the world slows and the universe feels closer. In the daytime, questions like what is space-time may feel intimidating, too large, too abstract, too far removed from ordinary life. But here in the softness of evening, the question becomes almost meditative. It invites you not to solve it, but simply to wonder at it. Because wonder is its own kind of understanding. So let this first part of our journey settle into you like a quiet realization. We live inside something we cannot yet describe. We travel through a medium we cannot see. We feel effects we cannot fully explain. And that is okay. The mystery of space-time is not something to conquer, but something to listen to softly, patiently, the way you might listen to the distant hum of the universe itself. Now, when you're ready, we will continue deeper, into the moment when a young patent clerk first dared to rewrite time. And as we drift deeper into this quiet mystery of space-time, our path gently leads us to a moment in history when a young man unknown, unnoticed, working far from any university, began to reshape time itself. Einstein in 1905. Special relativity and the collapse of absolute time. The year is 1905. Papers are stacked on wooden desks. Ink bottles glisten faintly in the afternoon light. And in the middle of this quiet room sits a 26-year-old clerk named Albert Einstein, his eyes soft but restless, drifting far beyond the walls around him. Most revolutions begin with noise. Einstein's began with silence. At this time, he was not a university professor. He had no laboratory, no funding, no academic position. He worked in the Swiss patent office examining technical documents for inventions he did not build. Every day he walked along the same quiet streets, past the same shops and trams, listening to the same familiar bells echo across Bern. And yet behind this ordinary facade, his mind was circling a question so bold, so strange, that almost no one else dared to fully confront it. What is time? For centuries, people believed time was absolute, a single cosmic clock that ticked the same for everyone everywhere. It felt obvious, natural, unquestionable. But Einstein was willing to question even the obvious. And in 1905, he discovered something astonishing. The speed of light is always constant, no matter how fast you move, no matter where you are, no matter what direction you're traveling. This single fact flipped the universe upside down. Imagine sitting beside a river at dusk. The water appears to flow at different speeds depending on where you stand. But imagine a river that always keeps the same speed no matter how you move with or against it. A river that defies intuition. Light is that river. It refuses to slow down or speed up for anyone. And so Einstein asked the only question that made sense: if light will not change for us, must we change for the light? The answer was yes. Time must stretch, space must bend, reality must adapt to protect the speed of light. As soothing as a deep breath, this realization flowed through Einstein's mind, not as chaos, but as an elegant, unavoidable truth. If you move quickly, time for you slows down. If you race close to the speed of light, your seconds lengthen, your heartbeat quiets, your aging softens. This isn't science fiction. It is woven into the structure of reality. Even your height changes ever so slightly when your motion lengths contract along the direction of travel. If you could somehow accelerate close to the speed of light, you would watch the universe ahead of you flatten, while the galaxies behind you stretch into a red, fading glow. Einstein revealed something extraordinary. There is no single universal now. Two people standing in different places or moving at different speeds do not share the same slice of time. Their clocks, their rhythms, their present moments drift apart. The cosmos does not experience time as a rigid line. It is a web of interwoven timelines, each shaped by motion and gravity. Your now is not the same as the now near a distant star. Time is not absolute. It is personal. This idea gently loosens the grip of our old assumptions. As the night deepens, imagine this truth settling over you like a warm blanket. Your experience of time is unique to you, shaped by your motion through the universe. Even here on Earth, satellites orbiting miles above us tick at different speeds. Without correcting for relativity, GPS would drift by kilometers each day. Your phone only knows where you are because Einstein understood that time does not flow uniformly. And yet, when he first introduced these ideas, the world barely noticed. There were no headlines, no fanfare, just a quiet publication in an academic journal titled "On the Electrodynamics of Moving Bodies," a revolution disguised as stillness. Einstein's insight came not from complicated machinery, but from imagination, what he called thought experiments. As a student, he dreamed of chasing a beam of light, wondering what he would see if he could keep up with it. "If I pursue a beam of light," he once wrote, letting that hypothetical journey unfold in his mind. From those gentle, wandering thoughts grew an entirely new picture of reality. It is poetic to consider that the collapse of absolute time, the ending of an ancient idea, began with such simplicity. A young man alone at his desk, letting his mind wander as softly as a drifting cloud. Tonight, if your own thoughts begin to drift the same way, let them. Let your mind move through Einstein's discovery, not with urgency, but with curiosity. Imagine time as something flexible, flowing, capable of slowing or stretching depending on how you move through space. Imagine two travelers in different corners of the universe, each living in their own unique present moment. Imagine that every heartbeat, every breath, every step you take is guided gently by the architecture of space-time, responding quietly to your motion. Special relativity does not just explain the universe. It invites us to experience it differently. It reminds us that we are not separate from the cosmos, we participate in it. We reshape time simply by moving. We alter space simply by existing. Your life, your body, your moments are all part of this grand, fluid choreography. And so as you rest, allow one final thought to settle softly into your awareness. Time is not a river flowing past you. You are flowing through it, shaping it with every motion. The young patent clerk in 1905 did not just rewrite physics, he rewrote our relationship with reality. He showed us that the universe is far more flexible, gentle, and mysterious than we ever imagined. And in doing so, he opened the first door that would eventually lead us to space-time itself. When you're ready, we will continue this quiet journey into the moment Einstein realized that gravity too is not a force, but the bending of the very fabric of the cosmos. And just as Einstein reshaped our understanding of time with a single brilliant insight, another quiet realization began to dawn on him, one that would reveal gravity itself in an entirely new light. General relativity, gravity is not a pulling force. It is the curvature of space-time. Let us follow Einstein to the next turning point in his journey, a moment when he reimagined one of the oldest forces in the universe, gravity, a force so familiar that we hardly question it. The reason we stay grounded, the reason planets orbit, the reason stars burn, collapse and die. But Einstein saw something different, something beautifully simple yet profoundly strange. It began with a sudden thought that struck him one morning, a thought he later described as the happiest idea of my life. Imagine stepping off a rooftop, not falling, but floating. If you were to free fall, Einstein realized you would feel weightless. The ground might rush up to meet you, but in that moment of descent, you would no longer feel your own weight. And if you were inside a falling elevator, everything inside would float as if gravity had vanished. From this single gentle observation came one of the greatest insights in the history of science. Free fall is indistinguishable from weightlessness. This is the equivalence principle, the beating heart of general relativity. It tells us that gravity is not a force reaching out from massive objects to grab things and pull them down. Instead, gravity is a geometry, a bending, stretching, curving of space-time itself. This idea feels serene, almost like watching ripples spread across a pond. Imagine space-time as a smooth, flexible fabric. Place a heavy object, a star, a planet, even your own body onto that fabric, and it sinks in just a little. Now imagine rolling a marble across the surface. The marble doesn't head toward the heavy object because it is being pulled. It moves there because the fabric beneath it curves. Objects follow the curves of space-time. They are not being forced. They are simply flowing along the natural paths carved by mass and energy. Einstein's realization was both elegant and unsettling. If gravity is geometry, then the universe is not a stage, it is a living, shape-shifting structure. Every star bends space-time. Every galaxy twists it into spirals. Every black hole tears it into wells so deep that not even light can escape. And you too create a tiny dimple in space-time simply by being here. This insight, so calm and quiet in Einstein's mind, led to a revolution. From this principle, general relativity was born. The equations he wrote, often described as some of the most beautiful in science, predicted strange and fascinating behaviors that Newton's gravity could not explain. Take Mercury, the small and restless planet closest to the Sun. For centuries, astronomers noticed that its orbit shifted in a way that Newton's laws could not account for, a tiny anomaly, mysterious and persistent. Einstein's curved space-time explained it perfectly. Mercury was not misbehaving. It was following the natural curves around the Sun's immense gravitational well. Then came the bending of starlight. During a solar eclipse in 1919, scientists observed starlight passing near the Sun being deflected by precisely the amount Einstein had predicted. Light, though massless, followed the curvature of space-time just like planets and moons. It was a moment that transformed Einstein from an obscure clerk into one of the most celebrated thinkers in the world. Gravity, as he revealed, does not pull on light. Space-time simply guides light along its curved shape. And yet the most astonishing consequence of his equations was something Einstein himself did not fully believe at first: the existence of black holes. These were not merely dense objects, but places where space-time curved so severely that it created a point of no return, a boundary where time slowed, space compressed, and all paths led inward. A star collapsing under its own weight could fold itself into a region so extreme that the normal rules of physics began to break down. To Einstein, these objects felt too bizarre, too extreme, too unearthly to be real. But the mathematics said otherwise. Black holes were not optional fantasies, they were natural consequences of curved space-time. And decades later, observational evidence confirmed their existence. The flickering of distant quasars, the dance of stars around an invisible center, the shadow captured by the Event Horizon Telescope, a glowing ring of light bent by a ravenous, invisible object. All of it whispered the same truth. Einstein's vision of gravity was right. As you rest, let the beauty of this idea wash over you. Gravity is not a force tugging at your body. You're not being pulled. Instead, you are gently following the natural curves of the spacetime that cradles you. The Earth orbits the Sun not because of an invisible leash, but because the Sun shapes spacetime around it, creating a path the Earth naturally travels along. Even the flow of time slows near massive objects. Clocks on mountains tick faster than clocks by the sea. A black hole with its immense gravity stretches time so dramatically that a second near its edge could be years far away. The universe is not rigid. It breathes, it bends, it curves, it shapes itself around matter and energy. And in a quiet, poetic way, Einstein's discovery reminds us of something deeply human. We are not separate from the universe's architecture. We are woven into its geometry, participating in its movement, with every heartbeat, every step, every breath. Tonight, as you drift towards sleep, imagine space-time not as an abstract idea, but as a soft, endless landscape, gentle hills and valleys shaped by stars, planets, and galaxies. Imagine yourself walking through this landscape, each step following the curves of a cosmic fabric that has existed since the beginning of time. Einstein gave us a new lens through which to see everything. Gravity is the story of how space-time curves, and we are characters shaped by that curvature. With this understanding, we can now move quietly toward the next chapter of our journey into the birth of black holes and the decades of wonder, skepticism, and discovery that followed. And as Einstein's new vision of gravity began to settle into place, a universe shaped not by forces but by the quiet curvature of space-time, another question emerged from the depths of his equations, one so strange and unsettling that even he hesitated to believe it: the birth of black holes and decades of debate. In 1916, as World War I cast shadows across Europe, a physicist named Carl Schwarzschild sat beneath the cold skies of the Eastern Front, looking not at the battlefield around him, but into the very structure of space-time itself. Schwarzschild discovered something remarkable, a precise solution to Einstein's equations for the space-time surrounding a perfectly spherical mass. It was an elegant answer written with technical clarity, but carrying a secret, a boundary, a limit, a critical radius where the equations behaved strangely. Later it would bear his name, the Schwarzschild radius. If matter were compressed within this radius, space-time would curve so steeply that all paths, even those taken by light, would tilt inward. Nothing could escape. Everything would be trapped. Time itself would slow as it approached the edge. Schwarzschild had uncovered the blueprint of a black hole, but at the time no one, including Einstein, believed such objects could truly exist. They felt like mathematical curiosities, artifacts of extreme assumptions, ideas that belonged on paper but not in the heavens. Einstein himself wrote that there is no such thing in reality, a gentle refusal to accept something so profoundly strange, and yet the universe had already been building them. To understand how, imagine a massive star nearing the end of its life. For millions of years it burns through the hydrogen in its core, forging heavier and heavier elements. But eventually, it reaches iron, a dead end in stellar alchemy. The star's outward pressure fades. Gravity, relentless and patient, takes over. The star collapses. If the star is small enough, it stabilizes as a white dwarf or neutron star. But if the star is massive, many times the mass of our sun, gravity wins completely. It pulls harder, faster, deeper, until the collapsing core shrinks past the Schwarzschild radius, slipping into a place where the fabric of space-time no longer allows escape. In 1939, the young physicist J. Robert Oppenheimer and his colleagues calculated this process with astonishing clarity. They showed that under the right conditions the collapse is unstoppable. A star does not simply shrink, it disappears behind a boundary, where light, time and space are trapped. Oppenheimer had proven that black holes were not fantasies, they were the inevitable fate of massive stars. And yet the world was not ready to listen. For decades, black holes remained theoretical ghosts, too bizarre, too extreme, too unsettling for many scientists to accept. Even Einstein resisted the idea to the end of his life, believing that nature would somehow prevent such absurdities from forming. The cosmos, he thought, must be kinder, less violent, less extreme. But the universe is under no obligation to match our expectations. Then came the 1960s. New telescopes reached deeper into the sky, and with them came a discovery so bright it could not be ignored: quasars. Objects shining with the power of 1 trillion stars, yet contained within a space no larger than our solar system. Nothing known could produce such energy, nothing except matter falling into a supermassive black hole. Suddenly, black holes were no longer whispers. They were roaring beacons at the hearts of distant galaxies. Around the same time, mathematician Roger Penrose revealed a breakthrough. The formation of a black hole was not a delicate, unlikely phenomenon. It was robust, natural, a direct consequence of Einstein's geometry. The equations predicted in a mathematically rigorous way that once collapse began, a black hole's birth was unavoidable. Penrose's insights earned him the Nobel Prize decades later, and then came Stephen Hawking, whose brilliant mind illuminated the quantum edges of these cosmic abysses. Hawking showed that black holes were not silent tombs, but dynamic objects that could radiate energy and slowly evaporate, a paradox that would challenge the foundations of physics. By the early 1970s, theory, mathematics, and observations were converging. Black holes were no longer just possible. They were everywhere, scattered across galaxies, living at the centers of star clusters, hiding in the quiet corners of the Milky Way. They had become real. A new cosmic landscape emerged. Imagine just for a moment drifting near a black hole, not close enough to fall in, but close enough to feel its presence. Space stretches around you like a vast invisible whirlpool. Time slows, thickening like honey. Light curves in looping arcs pulled toward the dark center. The stars behind you distort into glowing rings, shimmering as though reflected in a cosmic mirror. This is not science fiction. This is the geometry of space-time under strain. Einstein's equations, once quiet and theoretical, had revealed a universe far more dramatic than anyone expected. Black holes became laboratories for the extreme places where gravity rules with unyielding force, where time trembles, where matter spirals in luminous vortices, where our understanding of physics teeters at the edge of the unknown. And yet, for all their violence, black holes carry a strange kind of beauty. They remind us that the cosmos is not static. It evolves, it collapses and rebuilds. It hides secrets in shadows and illuminates them with light bent into delicate arcs. Black holes are the punctuation marks of the universe, endings for stars, beginnings for questions. As you rest tonight, imagine the calm persistence of Schwarzschild, working through equations on the front lines, the quiet certainty of Oppenheimer as he traced the path of a dying star, the patient insight of Penrose revealing the inevitability of collapse, and the soft brilliance of Hawking listening to the quantum whispers around the event horizon. Their work stretched across decades, pulled black holes from the dark corners of theory into the very center of modern astronomy. The universe did not ask us to believe in black holes, it simply showed them to us one luminous clue at a time. And with this understanding in place, we can now drift into the next chapter of our journey, toward the moment we heard the universe vibrate, when space-time itself rang like a cosmic bell. And just when black holes seemed to be the quiet monsters of the cosmos, hidden silent, absorbing all light and sound, Einstein's equations revealed one more surprise. Under the right conditions, even darkness can make the universe sing. Gravitational waves, space-time truly vibrates. Let us journey into one of the most delicate discoveries in all of physics, evidence that space-time is not just a quiet curved stage on which the universe unfolds, but a living fabric capable of vibrating, like the surface of a vast cosmic ocean. These vibrations are called gravitational waves, and they are among the faintest whispers the universe has ever spoken. To understand them, imagine for a moment a still pond at dusk. You toss in a tiny pebble and ripples spread across the water, gentle and effortless. Now replace the pond with space-time itself, and the pebble with something unimaginably massive. Two black holes spiraling together, their orbits tightening until they collide in a burst of gravitational energy that shakes the very geometry of the universe. Those ripples expanding outward across billions of light years eventually reach Earth, so faint, so soft, so subtle that they deform space-time on our planet by a distance smaller than 1/10,000th of the width of a proton. A proton, the heart of an atom, already impossibly small. And yet the waves we detected were thousands of times smaller than that. This is the scale on which nature speaks to us, and we astonishingly learned how to listen. The detector that heard the universe breathe on. September 14th, 2015, a pair of enormous instruments in the United States stretches of vacuum tunnels, arranged in long, perfect L shapes, recorded a signal unlike anything ever seen before. These instruments were part of LIGO, the Laser Interferometer Gravitational Wave Observatory. Their purpose was simple, but nearly impossible to measure a vibration in space-time so small that even the slightest disturbance could drown it out. A passing truck, a gust of wind, a person's footsteps, even the gentle vibrations of Earth's crust shifting miles away could ruin the measurement. And yet on that quiet morning they heard something unmistakable. Two black holes, each more massive than our sun, had collided over 1 billion years ago, long before humans existed, long before Earth formed into its familiar shape, long before the Milky Way even completed its first rotation since that ancient moment. Their collision sent ripples outward, ripples in space-time itself, and those ripples travelled across the cosmos until they finally reached us. The detectors recorded a faint chirp, a rising, trembling note as the black holes spiraled closer and closer, merging in one final burst of gravitational energy. This sound was not carried by air, it was carried by the universe itself, a vibration of space-time singing through the fabric of existence. A prediction from Einstein whispered by the universe. What makes this discovery so soothing, so profound, is that Einstein predicted gravitational waves 100 years earlier. But even he doubted they could be detected. They seemed too faint, too delicate, like trying to hear a single raindrop fall in the middle of a storm. And yet in 2015 the impossible became real. The universe did not just curve, it moved, it rippled, it rang like a cosmic bell. Gravitational waves confirmed something extraordinary. Space-time is real, tangible, physical, not an abstraction but a fabric that can stretch, compress and vibrate. It is a medium like water or air, except deeper, woven into the essence of reality. Imagine waves passing through you right now, gently stretching and squeezing your body by distances too small to feel. You are floating in a cosmic sea always carried along by its silent rhythms. And for the first time in history, we have learned how to hear its music. Why this discovery matters. In the soothing quiet of the night, it's easy to overlook the significance of such a faint signal. But gravitational waves opened an entirely new sense, a new way of observing the cosmos. Before 2015, astronomy relied almost entirely on light. Telescopes captured photons emitted by stars, galaxies, and gas clouds. But black holes do not emit light. They are dark, silent, hidden. Gravitational waves allow us to see what light cannot reveal. They let us observe the invisible. Through these waves we can listen to black holes merging, neutron stars colliding, supernova cores collapsing, possibly even echoes from the earliest moments after the Big Bang. This is not just astronomy. It is cosmic listening, a way to let the universe speak for itself. The emotional weight of a whisper. There is something deeply poetic in the fact that the most dramatic collisions in the universe produce signals so faint that only extraordinary patience and precision can detect them. It reminds us that even the loudest cosmic events arrive gently when they finally reach us. This is how the universe communicates, through soft, ancient vibrations that travel unimaginable distances with perfect fidelity. As you breathe slowly, imagine the faint hum of gravitational waves passing through you. Imagine the universe itself expanding and contracting around you in rhythms older than the Earth. These waves are not dangerous nor chaotic. They are soft, steady, peaceful, like distant tides washing over the shores of reality. They remind us that we are connected to events far beyond our world. We are shaped by cosmic stories written billions of years ago. A new door opens. When LIGO detected that first chirp, it was more than a scientific achievement. It was a moment when humanity gained a new sense, a way of touching space-time itself. It was as if the universe had whispered, "I am not silent after all." Other detections followed. Mergers, collisions, stellar remnants spiraling into darkness. Each signal a tiny tremor from somewhere unimaginably far away. And with every ripple we detect, we grow closer to understanding what space-time truly is, not just a mathematical framework, but a physical entity that breathes, moves, and carries the memory of cosmic events across the vastness of the universe. As you drift towards sleep, let that idea rest gently in your thoughts. You live in a universe that moves with you, a universe whose fabric stretches under your feet, whose rhythms pass silently through your body, whose vibrations whisper stories older than time on Earth. Gravitational waves are not just discoveries. They are reminders that we are part of something vast, connected and alive. And with this quiet wonder settling into place, we can now drift toward the next chapter, where space-time finally becomes visible to the human eye. and after hearing the universe speak through the faint music of gravitational waves, humanity began to open its eyes to something even more astonishing. A moment when the invisible fabric of spacetime revealed its shape in a single glowing image, photographing black holes. Spacetime becomes an image. Let us drift into a moment that changed the way humanity sees the universe, a moment when spacetime itself, usually silent and hidden, allowed us to capture its form as an image. Not a simulation, not an artist's impression, but something real carved from light bent by gravity so intense that even photons struggle to escape. For more than a century, black holes existed only in the equations of relativity. They were whispered about in scientific papers drawn in chalk on blackboards imagined in the mind's eye of physicists. We believed in them because the mathematics was too elegant and too persistent to ignore. We inferred their presence from stars spinning around empty centers, from jets of energy blasting across galaxies from the strange distortions of light. But still we had never seen one. And then in April of 2019 the universe opened a window. The first shadow, M87. Across 8 telescopes scattered around the planet, from the deserts of Chile to the high peaks of Hawaii, from the plains of North America to the frozen air of Antarctica, a global collaboration known as the Event Horizon Telescope synchronized their observations with atomic precision. Together they formed a virtual telescope the size of the Earth, capable of resolving details finer than anything ever attempted. The target was a supermassive black hole in the galaxy M87, a cosmic giant more than 6 billion times the mass of our Sun. What they captured was breathtaking. A circle of fire glowing with gas heated to billions of degrees wrapped around a dark, silent center. This central darkness, the shadow, was not the black hole itself, but the region where light could no longer escape. Around it, photons swirled in a last desperate dance, spiraling along the curved geometry of spacetime like embers caught in a cosmic whirlpool. This was our first direct glimpse of a place where spacetime bends so sharply that even time itself slows to a trembling crawl. For the first time in human history, we saw gravity paint an image. Light, following curved paths. What made the image so extraordinary is not merely its beauty, but what it revealed: light bending exactly as Einstein predicted. The glowing ring was brighter on one side because the black hole's rotation dragged space-time with it, boosting the light coming toward us and dimming the light moving away. The ring's size matched the equation for the Schwarzschild radius with astonishing precision. This was not an artistic interpretation. This was not imagination. This was physics made visible. Einstein's mathematics rendered in real photons traveling across 55 million light-years. Seeing the image felt like hearing the universe speak in a language we'd only read about but never heard aloud. A second revelation, Sagittarius A Tall. 3 years later, in 2022, the Event Horizon Telescope offered us a second gift, the image of Sagittarius A, the supermassive black hole at the center of our own Milky Way. Much smaller than M8 in a 7-ton, but far more dynamic. It flickers quickly as gas orbits its event horizon in minutes rather than days. Capturing this image required extraordinary patience. It was like trying to photograph a flame while the wind constantly reshapes it. Yet the result was unmistakable. The same glowing ring, the same shadow, the same elegant geometry carved by gravity. Suddenly, black holes were not rumors or abstractions. They were places, visible, measurable, real. And through them, space-time became something our eyes could touch. Why these images matter. To the sleepy mind drifting gently beyond the concerns of the day, it may seem like just another scientific milestone, a beautiful picture, a step forward for astronomy. But it is far more profound. These images are the first time humanity has seen light bent into perfect arcs by gravity. Matter spiraling around the edge of a cosmic abyss. Space-time folded so deeply that paths of photons loop back on themselves, the very boundary where time and space lose their familiar meaning. For centuries, gravity felt like a simple force. Now we can see its curvature. The black hole's shadow is not a solid object, it is the shape drawn by the behavior of light in the strange geometry surrounding the event horizon. What we see is space-time's silhouette. It is the universe holding up a mirror to its own structure. A cosmic sunset that never ends. Imagine drifting near the edge of a black hole, not close enough to fall in, but close enough to feel the strange serenity of curved space-time. the light around you would bend into arcs wrapping over the sky like ribbons of amber. Every direction would seem to glow. Even behind you, the black hole would reflect the universe in luminous echoes, bending starlight into halos. It would resemble a sunset suspended in eternity, a cosmic ring of fire, a horizon that is not a horizon at all, but the boundary of the knowable universe. And now, thanks to the Event Horizon Telescope, we do not have to imagine. We have seen it, a triumph of patience and whispered distances. What makes these images soothing, even meditative, is the quiet triumph they represent. Thousands of scientists, dozens of countries, and 8 observatories paused together, synchronized by the steady rhythm of atomic clocks to listen to the faint whispers of light that had traveled millions of years. The photons that formed the first image of M87 began their journey long before human beings walked upright. They crossed interstellar clouds, drifted through cosmic dust, avoided collisions with wandering stars, and finally met our telescopes, completing a voyage older than humanity itself. And we caught them. We captured their message. We turned their story into an image, a portrait of Spacetime. Spacetime revealed. These photographs confirm something quietly profound. Spacetime is not just equations, not just a theory, not just a metaphor. It is a real physical entity, one that bends, twists, folds, and glows through the behavior of a light around black holes. To see spacetime is to see the universe's true architecture. To witness its curves is to glimpse the blueprint of reality. As you drift towards sleep, let that thought become gentle within you. You live in a universe where even darkness can shine, where gravity can draw shapes in light, where space-time can paint its own portrait across millions of years. And with this quiet understanding, we can begin our slow descent into the next chapter of our journey, where space-time reveals itself not just in distant galaxies, but in the everyday workings of our lives. And as breathtaking as it is to see space-time revealed in the glowing rings around distant black holes, its quiet touch is not limited to the far edges of the cosmos, because space-time is here with us, shaping the rhythms of our everyday lives in ways so gentle we rarely even notice. Space-time in everyday life. It is easy to think of relativity and space-time as abstract ideas that belong to astronomers, physicists, or distant stars, but the truth is far more intimate. Space-time is woven into your routines, your technology, your senses, even the colors you see. You're drifting in space-time every moment of your life, and it is guiding you in quiet, invisible ways. To understand this, imagine yourself standing in an open field looking up at the sky. GPS satellites orbit high above you. 24 tiny machines, each about the size of a small car, circling Earth with quiet precision. They move fast. They feel less gravity than you do on the ground, and because of this, their clocks tick at a different rate than yours. Their time moves a little faster. This is not metaphor, it is not theory. It is relativity, Einstein's insights gently stretching time in orbit. If GPS satellites used ordinary clocks, your phone's location would drift by kilometers each day. Your navigation app would show you in the wrong city. Delivery trucks would route themselves into rivers. Airplanes would land on the wrong side of the runway. The entire system would collapse under the weight of its own inaccuracy. So engineers do something almost magical. They correct each satellite's time so that it stays synchronized with Earth's slower clocks. Every time you request directions, every time you track a package, every time an airplane lands safely, space-time is quietly doing the math. The very same equations that describe black holes, cosmic curvature, and gravitational waves are working behind the scenes to help you find your way home. Space-time is not distant. It is helping you navigate your neighborhood. Relativity in the color of gold. Now look at something simple, a piece of gold jewelry. Notice its warmth, its soft glow, its unmistakable yellow tone. Gold stands apart from other metals. Silver shines cold and white. Platinum glows with quiet sharpness. But gold radiates with a warmth that feels almost ancient. This color comes from relativity. Electrons in gold move extremely fast, so fast that relativistic effects shift the wavelengths of light they absorb. Rather than reflecting pure white light, gold absorbs some blue wavelengths and reflects richer, deeper yellows. Without Einstein's equations, gold would not be gold. It would shine white, losing the warmth that has captivated humanity for thousands of years. Space-time gives gold its color. Mercury's gentle liquid mystery. Now think of Mercury, the only metal that flows like water. Its shimmering surface reflects the world in a trembling silver pool. Mercury refuses to solidify at room temperature because its electrons obey relativity. Their high-speed motion changes how they bond with one another, weakening the grip between atoms and allowing them to slide freely. Relativity makes Mercury liquid. Without it, thermometers, barometers, and centuries of science would look very different. High-speed internet and time itself. Even the invisible signals racing through fiber optic cables depend on the synchronization of time. High-speed internet, financial transactions, communication networks, and global broadcasting all require clocks to beat in perfect harmony across continents. But clocks on Earth do not all tick at the same rate. A clock at sea level experiences more gravity and runs slightly slower. A clock in a skyscraper experiences less gravity and ticks slightly faster. A clock on a mountain top runs differently still. Relativity gently shifts time in every direction. To keep the world connected, to keep data flowing from country to country, to keep the heartbeat of the global economy steady, engineers constantly adjust for these small differences. Every video call, every online message, every streamed movie depends on our understanding of space-time. The internet is not just wires and light. It is a symphony conducted by relativity. A universe that touches everything. As you listen, let yourself feel the quiet wonder in this idea. The same equations that describe black holes bending galaxies are at work in your everyday life. The same mathematics that tells us how starlight curves around a cosmic abyss is used to help your phone know where you are. The universe does not keep its mysteries locked away. It invites us to experience them softly, continuously, effortlessly. Every second, every heartbeat, every step you take is guided by the geometry of space-time. And even though we cannot feel that curvature directly, we see its fingerprints everywhere. In the navigation systems that guide you home, in the golden glow of jewelry, in the liquid shimmer of Mercury, in the synchronized clocks that stitch the world together, relativity is not distant or abstract. It is intimate. It lives in your pocket, in your jewelry box, in your communication networks, in your sense of place on Earth. A quiet comfort in cosmic connection. There is something deeply comforting in knowing that your daily life is connected to the universe in this way. You may never notice the time dilation happening overhead, or the relativistic shifts in the metals you see. But these subtle effects are always there, flowing through the edges of every moment. It means you're never separate from the universe. You're never detached from the cosmic fabric. You're living inside the same geometry that shapes stars and galaxies. Tonight, as the quiet of the evening surrounds you, imagine Earth floating gently in space-time, its clocks ticking at different rhythms, its satellites gliding in smooth arcs, its people moving through curved geometry without ever feeling its touch. Imagine that every breath you take happens against the backdrop of a universe that bends, stretches, and reshapes itself in response to matter and motion. And now let that thought relax something inside you. The same laws that govern the vast, mysterious cosmos are guiding you through your daily routines. The universe holds you in its mathematics. It cradles you in its curvature. It walks beside you in every moment, quietly shaping the world you know. When you're ready, we can continue the journey into the deeper mysteries of what space-time might truly be made of. And as comforting as it is to see space-time woven quietly into the routines of our daily lives, there remains a deeper question, one that hums beneath every discovery we've made so far. What is space-time actually made of? Mystery number 1, what is space-time made of? We speak of space-time as a fabric, a geometry, a smooth continuum stretching across the universe. We describe how it bends, curves, ripples, and stretches. We draw it as grids, surfaces, and diagrams. But beneath these metaphors lies a question as soft and elusive as a dream. Is space-time a thing? Or is it only the shadow of something deeper? Einstein gave us the tools to understand how space-time behaves, but even he never truly explained what space-time is. And now, a century later, physicists stand at the edge of this mystery, exploring 3 profound possibilities, each breathtaking, each incomplete, each offering a glimpse into the foundations of reality. Let us wander gently through them, one at a time. 1. Loop quantum gravity, the universe made of tiny volume particles. Imagine for a moment floating through the emptiness between galaxies. You might feel as though space is infinitely smooth, a silent ocean, without texture or boundary. But loop quantum gravity suggests something extraordinary, that if you could shrink yourself trillions of times beyond the size of an atom, you would discover that space-time is not smooth at all. Instead, it would shimmer with structure. It would be made of tiny, discrete units, atoms of space microscopic loops woven into a delicate network. These loops form the smallest possible volumes of existence, so tiny that they cannot be divided further. Just as matter is built from atoms, space-time itself would be built from indivisible grains. At this scale, space would no longer look like a continuous fabric. It would flicker like pixels on a cosmic screen. In this view, gravity is not the smooth curvature Einstein described. Gravity emerges from the way these loops twist, connect, and vibrate. The curvature of space-time becomes a kind of quantum choreography. It is a beautiful idea, one that preserves the whisper of geometry while grounding it in quantum discreteness, and yet it remains unproven. The loops are far too small for current experiments to detect. The universe keeps this secret folded tightly within its smallest scales. 2. String theory and M theory. Space-time emerging from vibrating strings. Now imagine drifting through a deeper layer of reality, where everything you see, particles, forces, even. Space-time emerges from something even more fundamental. Tiny vibrating strings. In string theory, the universe is not built from point-like particles, but from minuscule filaments of energy. These strings can vibrate in different patterns, like the strings of a violin. Every pattern corresponds to a different particle. One vibration becomes an electron, another becomes a photon, another becomes a quark, and space-time. Space-time is not an ingredient, it is a consequence. According to this theory, space-time emerges from the collective behavior of strings, vibrating in higher dimensions, dimensions curled so small and subtle that we do not experience them directly. Like the hidden layers of a dream, these extra dimensions shape everything we see, even though they lie beyond everyday perception. In its grandest form, known as M theory, the universe might contain vibrating sheets, membranes, and 11-dimensional structures. The fabric of space-time becomes a vast flexible stage built from the harmony of these deeper entities. This view is sweeping, elegant, and hauntingly beautiful. A universe born from music. And yet string theory too remains unproven. Its scales are so tiny, its energy so immense that experiments are still far from detecting the strings directly. For now they remain mathematical whispers, compelling, poetic, but elusive. 3. EPR, space-time as a shadow of quantum entanglement. Now we drift into the most mind-bending possibility of all, an idea so new, so radical, that it reshapes the way we think about space itself. EPR. A simple equation proposed by Leonard Susskind and Juan Maldacena, carrying a profound idea. Space-time may be woven from quantum entanglement. In this view, space is not fundamental. Distance is not fundamental. Geometry is not fundamental. What is fundamental is connection. Quantum entanglement. The mysterious link between particles that remain correlated no matter how far apart they travel may be the thread from which space-time is stitched. The more entangled the quantum bits are, the closer the regions of space appear. If the entanglement weakens, distance grows. Space becomes a shadow cast by the deeper structure of quantum information. Even wormholes, bridges connecting distant points, might be nothing more than entanglement drawn on a cosmic scale. In this picture, the universe is not a physical arena, but a vast network of relationships. Reality becomes relational, geometry becomes emergent, space-time becomes a story told by quantum entanglement. This idea is bold, audacious, and while it beautifully ties together quantum mechanics and gravity, it is also still unproven, a mystery that cradles us. Tonight, as you drift toward rest, let this thought settle gently within you. We do not yet know what space-time is. We know how it bends around stars. We know how it ripples when black holes collide. We know how it stretches time, shrinks distances, and guides the paths of light. We know how to measure it, use it, navigate through it. But its essence, the thing beneath the equations, beneath the grids, beneath the metaphors, remains hidden. And there is something soothing, even comforting, in that mystery. The universe is not a solved puzzle. It is a living question, a gentle invitation to wonder. You right now are floating inside a medium whose true nature has not yet been revealed, and yet it holds you, guides you, and shapes every moment of your life. Perhaps space-time is made of loops. Perhaps it emerges from strings. Perhaps it arises from entanglement itself. Or perhaps the truth is something no one has imagined, but the mystery is not a barrier. It is a doorway, a reminder that the universe still has secrets to share. When you're ready, we can drift deeper still into the next question, where the origins of space-time lead us back to the beginning of everything. And once we begin to wonder what space-time is made of, it becomes impossible not to turn our gaze toward its beginnings, to the moment when space-time itself first unfurled, carrying the newborn universe into existence. Mystery. What really happened at the Big Bang, the Big Bang? Our cosmic dawn is often described as the beginning of everything, but what we truly know about this moment may surprise you. The story we tell in textbooks usually begins 380,000 years after the Big Bang, when the hot fog of plasma finally cooled enough for atoms to form and light to travel freely. That ancient light, stretched by billions of years of cosmic expansion, now reaches us as the soft microwave glow known as the cosmic microwave background, a delicate afterimage of the early universe. But this is not the beginning. It is only the first moment we can actually see. The true beginning lies hidden behind a curtain of heat and density so extreme that our equations fail. Einstein's general relativity, for all its power and elegance, leads us toward a point of infinite density and zero volume, a mathematical singularity. But infinities in physics are a sign of missing understanding, not actual physical states. And so the first moment of the universe remains shrouded in mystery, where our knowledge grows faint. Imagine the universe compressed into a region smaller than an atom. Temperatures beyond imagination. Energy so intense that the forces of nature, gravity, electromagnetism, the nuclear forces merge into one. Space and time lose their meaning. Quantum fluctuations ripple through everything like the tremble of a dream. At this scale, Einstein's equations break down. Our theories no longer know how to speak. This is where we stand at the threshold of the unknown, peering into a darkness we cannot yet illuminate. And yet physicists have not stayed silent. They have ventured forward with bold ideas to understand the moment when everything began. Inflation, a rapid, mysterious expansion. One of the most successful attempts to explain the early universe is the theory of inflation. It suggests that in the tiniest fraction of a second after the Big Bang, the universe expanded faster than the speed of light, not because objects were moving through space, but because space itself was stretching. This rapid expansion explains why the universe appears so smooth and uniform, why distant regions share the same temperature, and why the cosmos looks flat on the larger scales. Inflation solves many puzzles, but it introduces new ones. For inflation to begin and to end just the right way, the universe must have started in a very specific state. Physicists cannot yet explain why. It feels like walking into a room and finding a pendulum balancing perfectly upright, not impossible but deeply improbable. Something must have placed the early universe in that delicate position. Inflation is a beautiful answer, but not a complete one. A universe that bounced. Some theories suggest a gentler beginning. Instead of emerging from nothing, perhaps the universe once contracted, slowly tightening, like the breath before a sigh, and then bounced, expanding outward in a renewed burst of energy. In this picture, the Big Bang is not the true beginning, but a transition one cycle in a long chain of cosmic rebirths. Space could have been collapsing, shrinking into a dense hot phase, before reversing its motion and unfolding into the universe we know today. A cosmic heartbeat, a universe inhaling and exhaling across eternity. Such models avoid the singularity and allow space-time to pass smoothly through the moment of highest density. But they require forms of matter and energy we have not yet observed. They remain beautiful possibilities waiting for evidence. The multiverse one pocket among many. And then there is the most astonishing idea of all, that our universe might be one bubble in a vast cosmic foam. In some versions of inflation, space doesn't stop expanding everywhere at once. Instead, pockets of space stop inflating and form individual universes like droplets, condensing out of an endless mist. Each bubble could have different physical laws, different constants, even different dimensions. If this is true, then the Big Bang was not the birth of everything, only the birth of our particular universe. An island in an infinite sea, a page in a book with countless chapters, a single spark in a storm of cosmic creation. We may never visit another bubble, but if the multiverse exists, then the story of creation becomes far richer, far stranger, and far more gentle than we ever imagined. Our universe becomes a child of something larger, something that may itself have no beginning or end. Why this mystery matters. As you rest, let your mind soften around this truth. We do not know what happened at the Big Bang. And yet this uncertainty is not frightening. It is calming, even humbling. It reminds us that the universe is not a solved puzzle, but a living mystery. It invites us to explore, to imagine, to listen for the quiet clues hidden in starlight and cosmic echoes. The questions lingering around the Big Bang are not just scientific, they are deeply human. Where do we come from? Why does the universe exist at all? What shaped the first moment of time? Could there have been something before the beginning? The answers remain beyond our reach, like stars shimmering just above the horizon. But the act of wondering brings us closer, not in knowledge, but in connection. For in seeking the universe's origin, we discover a deeper truth: we are part of a story still unfolding, a beginning that lives within us. Every particle in your body was forged in the early universe. Every atom, every breath, every heartbeat carries the echo of the Big Bang. You are not separate from the cosmos, you are its continuation. A momentary ripple in a story, 13.8 billion years long. Tonight, as you drift towards sleep, imagine the early universe not as a violent explosion, but as a quiet unfolding, a soft bloom of space-time expanding from a single shimmering seed. Picture galaxies forming like petals, stars lighting like candles, planets cooling like stones beneath a cosmic tide. Feel in a gentle way that the entire universe once existed in a form so small it could fit into a space smaller than anything we can visualize, and that out of that moment came everything you have ever loved or known. We do not yet understand the beginning, but we are living inside its legacy, and as we consider the mysteries surrounding the universe's beginning, we inevitably turn our attention to the objects that guard its deepest secrets, black holes, whose very existence forces us to confront a paradox at the heart of reality itself. Mystery in none 3. Do black holes destroy information? Do black holes destroy information? It seems simple, but this question touches the deepest fabric of reality. It asks whether the universe keeps a perfect memory of everything that has ever happened, or whether some things vanish forever, erased from existence. This is the essence of the information paradox, a problem so profound that Stephen Hawking spent much of his life trying to unravel it. Where the paradox begins. Imagine a star collapsing into a black hole. All the information that describes the star, its temperature, its magnetic fields, the distribution of its atoms, its photons and particles falls with it beyond the event horizon, the boundary from which nothing can escape. In classical physics, that information is simply trapped, locked away, inaccessible but not destroyed. But Hawking discovered something surprising. Hawking radiation. Black holes slowly evaporate. In the 1970s, Hawking combined quantum mechanics with the curved space-time around a black hole and found that black holes are not perfectly black. They emit a faint thermal glow called Hawking radiation. This radiation is completely random, like the gentle hiss of static on an old radio. As the black hole radiates, it slowly loses mass. As it loses mass, it shrinks. And after an unimaginably long time, it evaporates entirely. But here lies the paradox. If a black hole evaporates into random radiation, what happens to the information that fell inside? Quantum mechanics sees information can never be destroyed. Its evolution must always be reversible. This rule is called unitarity, the bedrock of quantum theory. Yet Hawking's calculations suggested that information was lost, forever erased from the universe. This is not just a puzzle. It is a contradiction between the two greatest theories in physics, general relativity and quantum mechanics. The universe cannot obey both completely unless something deeper ties them together. The holographic hope. Physicists struggled with this paradox for decades. Some believed information was somehow preserved inside a remnant. Others thought it might escape in subtle correlations within Hawking radiation. Some even speculated that information slips into another universe entirely. But in the 1990s, a beautiful idea emerged, one that changed everything. The holographic principle proposed by Gerald 't Hooft and expanded by Leonard Susskind suggests that everything inside a region of space can be fully described by information encoded on its boundary, not inside, but on the surface, like a hologram. In this view, the three-dimensional world we experience might be a projection of information stored on a distant lower-dimensional boundary, and black holes were the first hints of this cosmic holography. Their event horizons, their surfaces hold all the information about what falls inside. This means that even if a black hole evaporates, the information is not lost. It is stored on the surface and slowly released through Hawking radiation. A black hole becomes a storyteller. Its radiation becomes a message. The universe becomes a keeper of memory. The Island Revolution, Seth 19 to 2020. For decades, the holographic solution was compelling but incomplete. It lacked a mathematical framework that could fully reconcile Hawking's evaporation with unitarity. Then came the breakthrough. In 2019 and 2020, physicists introduced what is now called the island theory. This new idea uses tools from quantum gravity and holography to show mathematically and beautifully that information is not lost when a black hole evaporates. In this model, parts of the black hole's interior become islands inside the quantum entanglement structure of the Hawking radiation. These islands act as bridges, allowing information to gradually leak out, not randomly, but encoded in a subtle, precise way. It is as though the universe found a loophole in the rules. Information is hidden, at first, then slowly woven into the radiation that escapes. The paradox dissolves. Quantum mechanics is preserved. General relativity remains intact. And deep beneath both theories lies a unified truth. Why? This paradox matters. As you drift into the gentle quiet of the night, you may wonder, why does any of this matter? Because the information paradox is not just about black holes. It is about the foundations of reality. It asks, can the universe forget? Is information eternal? What is the true nature of space-time? How do gravity and quantum mechanics fit together? These questions shape the search for quantum gravity, the long-sought theory that would unify Einstein's smooth space-time with the jittery probabilistic world of quantum mechanics. Solving the information paradox is one of the strongest clues we have to that unification. It tells us the universe is consistent. It tells us quantum mechanics still holds even at the edge of a black hole. It tells us space-time is woven with information at its core. A comforting thought before sleep. Tonight, let yourself rest in the quiet reassurance that the universe keeps its stories. Nothing is lost. Nothing is erased. Even in the darkest corners of space-time, information finds a way to survive. Just as your own memories, fragile shimmering, carried across years shape who you are, the universe too carries its memories forward, encoded in its geometry, radiation, and quantum entanglement. In the soft edges of the cosmos, nothing fades into true silence. Everything leaves a trace. Every particle has a history. Every event leaves a whisper. And perhaps in some deep and gentle way, the universe remembers itself through us, as beings who wonder, who question, who dare to listen to the quietest mysteries. And once we realize that information can survive even the depths of a black hole, a quieter, deeper question begins to rise, one that gently asks whether the very stage on which the universe unfolds might not be truly fundamental at all. Could space-time be an illusion? What if space-time, this vast stretching fabric that holds galaxies in their slow spirals and guides the paths of stars and planets, is not fundamental? What if space and time are not the bedrock of existence, but instead emergent like patterns rising from something deeper? This idea may seem strange, even unsettling at first, but approach it gently as you might approach the edge of a quiet lake at dusk, letting its reflections shimmer in your mind without rushing to grasp them. A universe built from information. In recent years, a growing number of physicists have begun to suspect that space and time are not primary ingredients of the universe. Instead, they may arise from a more basic element, quantum information. This is the same kind of information that appears in entanglement, where two particles, no matter how far apart, remain mysteriously connected. At the quantum level, the universe is not a collection of objects in space. It is a web of relationships, a vast, intricate network of correlations and interactions. Space-time in this view is not something the universe has, it is something the universe does. Just as music emerges from vibrating strings, just as consciousness emerges from billions of neurons, space-time may emerge from trillions upon trillions of quantum bits combining in just the right way. The heat analogy. Something from nothing. To understand this idea, gently imagine something familiar: heat. At the molecular scale, there is no such thing as heat. There are only molecules moving, some faster, some slower. Heat is not a fundamental object. It is a property that appears only when many particles interact. Space and time may be similar. At the deepest level, there may be no here or there, no before or after. Instead, these concepts arise only when countless quantum bits fuse into a coherent structure. The illusion becomes so perfect, so seamless, that we take space and time for granted. But beneath them lies a more primitive reality, entanglement as the architect of space. Several groundbreaking studies suggest that entanglement, the mysterious link between quantum particles, may be the true architect of space. When many particles become entangled in a specific pattern, distance emerges, geometry emerges, even the smoothness of space-time emerges. In this picture, the universe is not a stage. It is a relationship. Imagine a tapestry woven not from thread, but from connections, each link forming a point in space, each cluster forming a region, each network giving rise to the shape of the cosmos. If those connections weaken or vanish, the space between them collapses. Distance dissolves. Space is not a container. Space is a consequence. Time as an emergent flow. And what about time? Time too may be emergent. Not a fundamental river flowing forward, but the appearance of order in a complex network of quantum information. When correlations build in a specific direction, we experience that direction as time's arrow. Past and future emerge from deeper patterns. Moments crystallize out of quantum structure. In this sense, time is not something the universe moves through. Time is something that arises when the universe organizes itself. A universe without space-time. If we could somehow zoom far enough into the fabric of existence, space-time might dissolve like zooming in on a digital photo until the smooth curves break into pixels. At this scale, there is no continuous space. There is no flowing time. There is only quantum information. Space-time becomes a large-scale illusion, a story the universe tells when enough quantum bits join together. This does not make space-time any less real to us, just as a rainbow is real, even though it is not a physical object. It is an emergent phenomenon, beautiful, meaningful, and dependent on deeper laws. Why? This idea is so transformative. If space-time is emergent, the entire structure of physics changes. Einstein's equations, as beautiful as they are, become approximations like the laws of fluid dynamics, which describe water without describing the molecules that make it flow. Gravity itself becomes emergent, arising from the deeper interplay of information. The boundary between quantum mechanics and relativity begins to blur. A unified theory, quantum gravity, becomes possible. The conflicts and paradoxes dissolve, revealing harmony beneath. This idea does not diminish Einstein's work, it completes it. A gentle shift in perspective. Tonight, as you listen in the softness of the evening, allow yourself to imagine the universe not as a cold mechanical grid, but as something more alive, more connected, more relational. Imagine space-time as the shimmering surface of a deep ocean, calm, smooth, familiar, but beneath that surface lies a vast and intricate world of currents, pressures, and patterns. The waves you see are real, but they are not the whole story. Space and time may be the waves. Quantum information may be the ocean. The universe is richer, deeper, more mysterious than we ever imagined. And yet this mystery is comforting, because it tells us that the cosmos is built not from empty space, but from connection. Nothing exists in isolation. Everything is part of a larger network. Even the space between stars is the product of something deeper, a comfort in the unknown. Let yourself drift into this thought. If space-time is an illusion, it is the most beautiful illusion. Imaginable, one that allows galaxies to swirl, planets to orbit, and consciousness to arise. One that allows love, memory, hope, and dreams to unfold within the gentle rhythm of time. We do not yet know what lies beneath this illusion, but the universe invites us to keep wondering, and perhaps in the quiet hours of the night that is enough. Philosophical and technological implications. Over the past few chapters, we have followed Einstein's footsteps, watched stars collapse into black holes, listened to the universe vibrate, and traced the hidden patterns of quantum information beneath the surface of reality. Now, standing at this threshold of understanding, we can gently ask, what happens if we truly understand space-time? What doors might open? What dreams might become real? Let's wander through these possibilities slowly, like walking through a quiet observatory under a dome of stars. 1. The technology of gravity, a future. Shaped by curvature, gravity in Einstein's universe is not a force, it is geometry. To control gravity would mean learning how to sculpt spacetime itself. This sounds impossible now, but so did electricity 2 centuries ago. So did flying, so did capturing the shadow of a black hole. If spacetime is a fabric, perhaps someday we will learn to tug at its threads. Imagine spacecraft gliding by, bending spacetime rather than burning fuel, energy generated from the controlled movement of curvature itself, structures protected from gravity through geometric manipulation. These ideas live at the boundary between speculation and possibility, but they are grounded in the physics we already know. Gravity is not magic, it is shape. If we understand the shape fully, we may someday learn to guide it the way we guide electric currents. Humanity might harness gravity the way sailors harnessed wind, not by conquering nature, but by learning its patterns. Such technologies would not be loud, violent, or forceful. They would be silent, smooth, elegant, true children of space-time. 2. New forms of energy extracting power from the structure of the cosmos. If space-time has structure, quantum, geometric, or informational, then that structure contains energy, perhaps vast amounts of it. Physicists have long speculated that the vacuum of space-time holds immense energy, what we call zero-point energy, the restless hum of quantum fluctuations. And while the path to harnessing such energy remains unknown, understanding space-time could give us the map. Imagine clean, abundant energy drawn from the quantum fabric itself. New states of matter unlocked by extreme curvature. Energy generation that mirrors the processes inside stars. Such possibilities no longer feel purely fictional when we consider that black holes themselves release vast amounts of energy when particles orbit near their horizons. The universe does not hide its power. It displays it in every galaxy, every cluster, every cosmic collision. We have only to understand the blueprint. 3. Communication. Through space-time beyond the speed of light. The speed of light is a cosmic speed limit, at least within space-time as we know it. But what if space-time is not fundamental? What if information is stored deeper, woven in ways we have yet to understand? Some theories suggest that entanglement connection between particles across any distance may allow for new forms of communication. Not faster than light messaging, but something more subtle communication through the structure of quantum information itself. If space-time emerges from entanglement, then entanglement may allow us to reach across it, not by breaking the speed of light, but by using a different kind of pathway, a connection woven beneath space-time instead of across it. Think of it like whispering across a bridge of quantum threads. Such communication could reshape science, medicine, exploration, and our understanding of consciousness. It would be quiet, instantaneous, and beautifully strange, like hearing an echo that crosses the universe without ever leaving your side. 4. Travel across space-time. The dream of the cosmic roadway. If gravity curves space-time, then controlling curvature may someday allow us to shape pathways through it. Wormholes. Once pure speculation are mathematical solutions to Einstein's equations. They might be unstable now, fragile, fleeting, but if space-time has an underlying quantum structure, perhaps future technologies could stabilize such passages. Imagine journeys between distant stars in moments rather than centuries, exploration of other worlds without crossing the empty space between them. A universe where distance is not a barrier but a choice. Even if wormholes remain forever out of reach, understanding space-time could lead to propulsion methods. We cannot yet imagine methods that ride the waves of the universe like surfers on a cosmic tide. Humanity might become a species not bound by its planet, but guided by the geometry of the cosmos itself. 5. Answers to the oldest questions. Time origins, endings. Perhaps the most profound implications are not technological at all. They are philosophical questions humanity has asked since the first fires burned in the first caves. Is time real? If time is emergent, then past and future may be fluid-shaped not by a river, but by patterns in quantum information. How did the Big Bang begin? If space-time is not fundamental, then the Big Bang may not have been the beginning, only a transition, a shift in deeper quantum structures. Do black holes end? If information survives within Hawking radiation or holographic geometry, then even the darkest objects in the universe may have an afterlife dissolving into information rather than vanishing. Understanding space-time could bring clarity to these questions, not through myth or metaphor, but through science spoken gently in the language of the universe, a universe that invites wonder. Tonight, settle into this quiet thought. Learning what space-time truly is would not simply expand our knowledge, it would transform our understanding of ourselves. We would see that we walk inside a cosmic structure we barely comprehend. Our lives unfold along patterns we did not design. Our minds are reflections of the universe that gave rise to us. Understanding space-time is not just a scientific pursuit, it is a quest to understand our place in existence. It is the soft realization that the cosmos is not distant or cold. It is a living, evolving tapestry, inviting us to slow down, breathe deeply, and listen to its quiet truths. As you drift toward rest, imagine the universe not as a machine but as a story, one written in the curves of space-time, the shimmer of quantum fields, the whisper of gravitational waves. The more we learn, the more the cosmos seems to draw us closer, not with force but with wonder, not with certainty but with possibility. And perhaps someday when we finally understand space-time, we will find that the answers were never separate from us. They were woven into the quiet geometry of our own curiosity. We stand at the edge of the unknown. Tonight, as the soft darkness folds around you and your breath settles into a slower, calmer rhythm, let us linger at the final doorway of our cosmic journey. A doorway Einstein himself opened more than a century ago. He led us to the edge of something enormous, something beautiful, something profoundly mysterious. Yet he also left us standing before a question so deep that it still humbles the greatest scientific minds of our time. What is space-time? Einstein gave us the language to describe its behavior. He showed us how it curves, how it bends, how it slows time and stretches distance. He revealed that gravity is not a force but a conversation between matter and geometry. He predicted ripples in space-time, the existence of black holes, the bending of light, the flow of time itself. But Einstein did not explain what space-time is. He brought us to the doorway and stopped gently at the threshold. Now, a century later, we stand where he stood, peering into the quiet unknown. A doorway built of questions. The beauty of science is not only in the answers it provides, but in the questions it illuminates. And few questions glow more softly, more enticingly than this. What lies beneath space-time? Is it made of loops, strings, quantum entanglement, something else entirely, something beyond anything we have imagined we do not yet know? But we sense more than ever before that space-time is not the end of the story, it is the beginning. Like the surface of a deep ocean, it ripples and bends in response to the forces below, gently revealing the presence of structures we cannot yet see, but can feel through mathematics and observation. Tonight, as you let your thoughts drift, imagine space-time as that shimmering surface, and imagine that we humans, scientists, dreamers, are leaning over the edge of a cosmic pier, gazing into water that holds mysteries stretching far below the reach of light. Einstein's gift and Einstein's silence. Einstein's theories transformed everything. Before him, space was a stage, time was a clock, gravity was a pull. After him, space and time became fluid, dynamic, interwoven. Gravity became curvature. The universe became a living fabric. And yet, when grappling with the origins of space-time, Einstein stepped back. His equations hinted at things he could not accept. Singularities, infinities, the birth of black holes. He sensed the limits of his own creation, the way an artist senses the edges of a canvas too small for the vision they hold inside. Einstein once said, "The important thing is not to stop questioning." And so, the questions continued without him. The scientists who followed today's physicists stand where Einstein once stood, but with tools he could never have imagined: telescopes that capture the shadows of black holes, detectors that listen to the vibrations of space-time, quantum theories that weave information into geometry, mathematical visions of universes beyond our own, computer simulations that trace the birth of galaxies. They stand at the threshold he built, but the door remains only partly open. Each new discovery reveals something extraordinary. The universe is stranger, richer, and more interconnected than we ever dared to believe. And still, the question lingers soft and persistent. What is space-time? This question pulls modern science forward, the way gravity pulls planets in their orbits quietly, unceasingly, gracefully. A universe that invites humility. There is something deeply comforting in knowing that even now at the height of human knowledge we remain surrounded by mystery. It reminds us that the universe is not a machine to be mastered, but a story to be listened to one page at a time. The more we learn, the more we realize how small and exquisite our understanding truly is. But this smallness is not weakness. It is connection. It is humility. It is the soft truth that we are part of something much larger, much older, and much more beautiful than ourselves. You lying here listening to the quiet flow of these words are part of that story. Your atoms were born in stars. Your mind holds the echoes of ancient cosmic processes. Your heartbeat is synchronized with the rhythms of space-time itself. You belong to this universe. You're woven into its fabric. You're in every sense a child of space-time, standing at the threshold. Imagine again that doorway Einstein brought us to. Imagine standing there, feeling the vastness of what lies beyond. Imagine the quiet electricity in the air, the sense that the next step, the next discovery could shift everything we know. We are closer now than ever before. With every gravitational wave we detect, with every black hole shadow we photograph, with every quantum equation we refine, with every particle experiment we conduct, with every whisper of entanglement we uncover, we inch toward that deeper truth. Perhaps the next breakthrough will reveal the structure beneath space-time, the code, the pattern, the quantum heartbeat of the cosmos. Perhaps it will show us how the Big Bang truly began. Perhaps it will allow us to unify quantum mechanics with general relativity. Perhaps it will open doors to new technologies, new ways of understanding, new ways of being. Or perhaps it will show us something entirely unexpected, something waiting quietly beyond the horizon of thought. A gentle ending to a vast journey. Tonight, as you drift towards sleep, let this final thought settle gently into your mind. We stand at the edge of the unknown, not in fear, but in wonder. The universe is not finished revealing itself. The story is not complete, the mystery is not solved, and that is its beauty. Einstein led us to the doorway of space-time. Now it is our turn to open it, to peer through, to listen, to learn. With patience, with curiosity, with awe, the next great discovery may come not with noise, but with a whisper, a soft tremble of space-time, a faint glow in a distant galaxy, a subtle equation scribbled on a quiet chalkboard, a signal woven into quantum information. It may come in a moment as gentle as breath, as small as a spark, as quiet as sleep. For now, rest in the knowledge that the universe is still unfolding, and we are here for the unfolding, standing at the threshold, bathed in mystery held in the soft, endless fabric of space-time. Good night, traveller of the cosmos.